Welcome everyone. So far we have discussed about the mix design procedure for making concrete mixes. Now we are going to discuss one of the problem based on the mix design. Okay. For this problem we have chosen M40 grade of concrete. Here we are going to use the IS 456 code and IS 10262 2019 code. Okay. So while referring these codes only, it will be helpful for you to design the concrete mix. Okay. So first they have given some of the data here. So they asked us to design the concrete mix for M40 grade of concrete using IS 456 2000 and IS 10262 2019. Okay. So they have chosen the type. In question they have told us to use the cement as OPC 43 grade cement. Okay. So they have assumed the maximum size of aggregate as 20 mm, and the exposure condition, that is the location where you're going to place is, and the exposure condition severe. Okay, severe, and also it is reinforced cement concrete. RCC means reinforced cement concrete, is not plain cement concrete. The degree of workability of the concrete according to the slump value is 100 mm. Okay, so the minimum cement content is given as 320 kilogram per meter cube, and the maximum water cement ratio is given as 0.45, and the method of placing of concrete is by pumping. So we know if you're going to construct some high rise buildings like tall structures, say if you're choosing on G plus 6 or G plus 7, means to the top floor you cannot take the concrete mix. It will be little difficult. Okay, by that time what we will be doing to transport the concrete is we will be pumping the concrete. Okay, so the method of placing of concrete here is also taken as pumping. If it is a pumping, means the workability will be little higher than normal placing of concrete. Okay, so the degree of supervision is often taken as good. It is also taken as good here. And the type of aggregate here they are using is crushed angular aggregate. We very well know that in construction they will be preferring only this crushed angular aggregate because of the interconnection between the cement matrix and the aggregate. Okay, so they have chosen the crushed angular aggregate. Since it is 20 mm aggregate, means they are going to make this mix design for some building works. Okay, so they have chosen the super plasticizers here. So they are going to use one of the super plasticizer. You write it down here itself. They are going to add the super plasticizer by 2% of the weight of the cement. Okay, super plasticizers will be added in this problem by 2% to the total weight of the cement. The specific gravity of the coarse aggregate is taken as 2.74, and also the specific gravity of fine aggregate is also 2.74. You know the specific gravity of cement, right? The specific gravity of cement is often taken as 3.15. Since it is a OPC cement, it is 3.15. Next, coming to the water absorption capacity for the coarse aggregate is 0.5 percentage, and for fine aggregate is 1 percentage. Next, grading of coarse aggregate. This is also important. Grading of fine aggregate, here they have chosen as zone 1. Okay, so we will be getting these values like that specific gravity of coarse aggregate, fine aggregate, and this grading values and all using some experiments in the laboratory. Okay, by that only we will be getting these values. It's not taken as simply given in the question itself. When you are making a mixed design, you will be having some materials, you will be having some collective of materials, cement, sand. So you have to study the properties of the cement before going for the mixed design. You will be conducting the specific gravity test for cement, will be conducting the specific gravity test for coarse aggregate and fine aggregate, then only you will be getting those values. Since this is a problem, they have given the values straight away. Okay, next moving on to the problem. So they asked us to design the M40 grade of concrete. So first step is to find the target mean strength of the concrete. For that we all know FCK dash is equal to FCK plus 1.65 S. Okay, let me tell what is that FCK dash. FCK dash means it is the target strength what we are expected at the 28 days. Okay, after making this design, mixed design, you will be casting that and then you will be testing that, right? So the 28 days compressive strength is expected to be that value, that is called as FCK dash. FCK is characteristic compressive strength, which is if it is a M40 grade of concrete, means its characteristic compressive strength, that is FCK, will be equal to 40 Newton per mm square. Am I right? So it is FCK is taken as 40. You know what is S? S is nothing but the standard deviation. Standard deviation according to the table 1 it is taken as 5 for M40 grade of concrete. Okay, so here the value is taken. So by using the values, you are getting the target mean strength as 48.25 Newton per mm square. Okay, when you are going to do this mixed design, the target strength will be around 48.25 Newton per mm square. Okay. So next, coming to the second step, that is the selection of water cement ratio. So it is given as 0.45 in the question. That is, they are told that it should be the maximum water cement ratio is taken as 0.45 in the question. But you see here, you have to choose the water cement ratio. For that, what we are going to do is we are going to refer IS 456 code book. In that, go to the table number 5. Okay, if you go to the table number 5, you can see the table like this in your code book. You'll be having the code book in your hand. You just refer that page. Okay, so you see here what they have asked is, this is for reinforced concrete. Wait, see, this is for reinforced concrete, this is for plain concrete. Our question is reinforced concrete, so we are going to see here, that is reinforced concrete. What are the three columns given here? Minimum cement content, maximum water cement ratio, minimum grade of concrete, and they have provided with 5 exposure conditions here. So in the second step, what we needed, we are going to find the maximum water cement ratio. For this reinforced concrete, they have given the extreme condition. So the value is 0.4. Have you all got it? So in the question, they have asked your second step is to find the water cement ratio. Right. To find the water cement ratio, you have to move on to the table number 5 in the IS 456 code book. When you are coming to that table, you can see the classification. One is for plain concrete and another one is for reinforced concrete. Since they have mentioned it as reinforced concrete in question, we are going for this reinforced concrete. We know the exposure condition as extreme. When corresponding to these both conditions, you are getting the water cement ratio value as 0.40. Is it clear? Okay, fine. So we have taken that 0.40 here. Okay, so it's less than 0.45. Obviously it is less than 0.5. 0.45 is given here. You can see in here the maximum water cement ratio in the question is given as 0.45, which means it should be the maximum. 0.45, above 0.45 it should not go. That is the concept. So it is less than 0.45. So our design is so far it's going good. Okay. Next, moving on to the step number 3, that is selection of water content. So you adopted the water cement ratio. Next, you are going to find the water content. After finding the water content, you will be calculating the cement content by using the water cement ratio. Okay, now let's discuss about the selection of water content. You just take the IS 10262 2019 code book. In that, you just go to the class 5.3. Class means the chapter number 5.3. There they have given some paragraph. When you read out that, you can understand one thing. Okay, so whenever the water content, whenever the slump value is increasing, actually what the concept is, maximum water content. Okay, they have generalized the water content as 186 liter. Okay, in the code book they generalized the water content as 186 liters. So they generalize the value as 186 liters. So for this 186 liters, they have given two conditions. One is the aggregate size should be 20 mm. Okay, and the slump value should be between 25 to 50 mm. Okay, for these two conditions, this is the condition number 1 and this is the condition number 2. That is for the aggregate size of 20 mm and the slump value of 25 to 50 mm only. They have generalized the maximum water content as 186 liters. Okay, but coming back to our question, wait. When you are coming back to our question, here you can see the slump value as 100 mm. Right. but the 186 liter is corresponding to only 50 mm. You don't want to bother about the maximum size of aggregate because it is in the question also it is 20 mm, but the slump value is only differing. Okay, for that we need to do one thing. So we have to, there will be some changes when the workability condition, that is when the slump value is getting changed. Let us see what is the change. You see here, so for every increase of 25 mm slump value, you have to increase the water content by 3%. Okay, for every 25%, 25 mm, okay, for every 25 mm increase in the slump value, you have to increase the water content by 3%. If the slump value is increasing, okay, water content is also increasing. Write down this point. You can refer this point in the class 5.3 of IS 1026/2019, and even this condition is also available in IS 456. Okay, so we have taken this, right? So for 100 mm slump, what happens? So this is for 50 mm. So here it is 100 mm. 50 plus 25, it is 75. Again, you have to multiply one more 25. So you are multiplying 225 mm to get this 100 mm slump. So 3 plus 3 percentage, that is here taken as 6 percentage. Okay, so you are going to add 6 percentage of extra water with respect to this 186 liters. So when you are doing that, you will be getting the water content as 197 liters. So you can ask, the generalized condition is for 20 mm aggregate, when the slump value is 50 mm, you will be having the water content as 186 liter. That is clear. But in our question, they have given us 100 mm. So we have to make some corrections in this value, in this 180 liters. Okay, what is that correction means? For increase of every 25 mm slump, the water content will be raised by 3%. Here the slump is increased by 50 mm. So I am increasing the water content by 6%. After doing that, I will be getting the water content as 197 liters. Clear? Next, coming to the superplasticizers. So you are adding superplasticizers, right? So it is a water reducing admixtures, we all know very well. So it is a high range water reducers also. So you have to think about this. You have to use this concept about the superplasticizers only when you are discussing about the water content. Okay, for that purpose only we have discussing about the superplasticizer. See, if they are not giving any superplasticizer in question, means you are not going to do this step. You will be getting the water content directly as 197 liters, and you can move on to the next step. Since they have given the superplasticizers is used, you are going to use this step. Okay, so you are going to use the superplasticizers. So you know it can be reduced up to 20% or above. Average they are taken as 20%. So here they are assuming as 29% reduction. We all know it is 30% reduction. Superplasticization means 30%. If it is a plasticizer means you will be taking as 15%. But here they are reducing it by 1% and they are just simply taking as 29%. This is your design. Okay, this is design. There is a difference between a design and analysis. Okay, in design, everyone will get every different values. Okay, the values should not be the same thing. Okay, but analysis is something different. So you may take here as 30% also, that is also not wrong. But you follow the same procedure, it will be helpful for you throughout your examination. Okay. So now I am taking as 29%. So I have to reduce the water content. This is your obtained water content, right? So this 197 liters will be reduced because of the superplasticizers. How much it is getting reduced means it is getting reduced by 29%. So it's a simple calculation. So I am doing that and I am getting the water content as 140 liters. Isn't it clear? Okay. Next, moving on to the calculation of the cement content. Here you can see you found the water cement ratio as 0.4. In question, you don't bother about the question now. In question, it is given as 0.45. But in your decide what you have found, that is your answer. Okay. So that is 0.4. You have to take that water cement ratio only. Okay. So you also found the water content as 140 liters. You know what is this water by cement ratio means? Water divided by cementitious material ratio. Okay, so you know the water content now. It is 140 liters. Divided by this water cement ratio will get the value of cement content. Okay, so I found the cement content as 350 kilogram per meter cube. Now what is my job is I have to check whether this cement content is permissible for making this concrete or not. Okay, so again where I am going means again I am going to the table 5 of IS 456. Let me show that. So you be clear here itself. Okay, so it is a 350 kilogram per meter cube is what you have found using the mixed design. Okay, so let us see in the table 5. See, this is for table 5 of IS 456. So I told you, right? So we are going to see only this reinforced concrete, that is for extreme condition. Okay, so the minimum cement content is 360. Okay, it is 360 kilogram per meter cube. Is it correct? No, because we have chosen here as a severe condition. It is not extreme condition. I have marked wrongly. See, in a question they have given the exposure condition as severe, right? For severe condition, the minimum cement content in the reinforced concrete is 320 kilogram per meter cube. You can see the unit here, 320 kilogram per meter cube. Okay, so again moving on to that slide. Now you see, this is 320 kilogram per meter cube according to the table 5 of IS 456. It's better to write the class number also here. Okay, often used to write the class number and the table number. Okay, so 320 kilogram per meter cube. What you have to do is you have to check whether this value is less than this 320. So here it will be 320. It should be greater than 320. So it's fine, your design is fine, you can proceed the design now. Next, coming to the fifth step, that is you are going to find the proportion of volume of coarse aggregate and fine aggregate. So you found the value of the cement content and the water content successfully. Next we are going to find the coarse aggregate and the fine aggregate. For that what you have to do is you have to check the zone in which the aggregate is falling down. Okay, it is falling in the zone 1. So we are all clear about that. Okay, when it is falling in the zone 1, you see here. See, this is zone 1. Okay, this is your aggregate size, which is 20 mm, zone 1. Okay, maximum nominal size of aggregate, volume of coarse aggregate per unit volume of total aggregate. Zone 1 is 0.60. This is how you are going to use the code book. Okay. So it is taken as 0.60. Volume of coarse aggregate is taken as 0.0 using the code book in the IS 10262. You note it here. This is table 5 of IS 10262. Whereas for cement, that water cement content, you have used the same table number 5, but it is in IS 456. Here it is IS 10262. Be clear with that. Okay. Next, you have to go through this point very well. Okay, see here the volume of the coarse aggregate required to increase the fine aggregate content, right? So as the water cement ratio is lowered by 0.1, the proportion of the volume of coarse aggregate is increased by 0.02. The thing is, so they will be using this value. Here you can see, okay, here in the heading you can see one more point here. You see this. What does that mean? So the water cement ratio should be of 0.5. So in the previous case, you noted this, right? That 186 liter corresponds to 50 mm slump, right? So here also this value, this volume of coarse aggregate corresponds to the water cement ratio of 0.50. But in your question, you are having the water cement ratio as 0.4 only. It is not 0.5. For that, we have to make some corrections in the design. You can take this value as 0.60. After taking that, you will be adopting some corrections in the design. Let us see what corrections we are going to do. That is what given here. As a water cement ratio is lowered by 0.1. You can see here with respect to 0.5, 0.4 is reduced by 0.1. Correct? The difference between the 0.5, 0.5 is the standard case. 0.4, that is a water cement ratio of 0.4 in your design is what you obtained. So that 0.5 minus 0.4 is 0.1. That is what given here. This 0.1 is that 0.5 minus 0.4. The proportion of volume of coarse aggregate increased by 0.02, which means you are going to increase this value. Okay, you are going to increase this value, that is that 0.60 by 0.02. Are you clear? So then you will be getting the water cement, the volume of the coarse aggregate as 0.62 after making that correction. Okay, so for every 0.10 decrease, you will be increasing the volume of the coarse aggregate by 0.02. Okay, so here it is decreased by 0.10. So I am going to add that 0.02 so that I got the value of 0.062. Sorry, 0.62. And one more thing, in the question they gave this as pumpable concrete. If it is a pumpable concrete means you have to, there will be some reduction in the volume of the coarse aggregate. Okay, so if this is the volume of the coarse aggregate is 0.62. In that you are going to reduce the 10% since this is a pumpable concrete. If it is a not pumpable concrete means you can skip this step. Okay, you can directly take the volume of coarse aggregate as 0.62. Since they have given this as pumpable concrete, we are going to reduce the volume of the coarse aggregate by 10%. So what is the value of the volume of coarse aggregate now? It is 0.56. Okay, so now the total volume of the aggregate is 1. In that you are going to deduct the coarse aggregate. Then you will be getting the fine aggregate value because you are using coarse aggregate and fine aggregate. Okay, both are equal to 1. So in that 0.56 is coarse aggregate and the remaining will be 0.44, that is the fine aggregate. Up to this it's clear. So we have found the volume of the coarse aggregate and fine aggregate. Next we are going to find the mix calculation. Okay, for that first you have to name the value. So you just name this as A, B, C, D and all. Then in later cases it will be helpful for you. So first they have given the volume of concrete. You have to choose the first. You will be designing the concrete for 1 meter cube volume. Okay, from that only you will be reducing the content according to your need. Okay, you will be often designing your concrete mix for 1 meter cube of volume of concrete. So A is taken as volume of concrete, that is 1 meter cube. Next, coming to the point B, it is the volume of cement. Volume of cement can be taken as mass of the cement divided by specific gravity of cement into 1000. For this you should know what is the specific gravity, what is the mass, what is the volume. So you know, right? What do you know? What is the unit weight? Unit weight is given as weight by volume, right? Weight is here taken as mass. We just keep it slim simply. Okay. So I'm just I know the volume. I'm just taking the volume here. This is mass divided by unit weight. This unit weight can be written as specific gravity of that material into specific gravity of water. This is not water. This is a unit weight of water. So it is the standard case. From this only they found this volume, mass of the cement divided by specific gravity of the cement into 1000. Okay. See here, you know the mass of cement. Okay, you know the mass of cement, we have found that as 350, right? So you know the specific gravity of cement also, it is 3.15. This is 1000. After substituting the value, you will be getting the volume of the cement. Similarly, you are going to calculate the volume of water. You know the mass of water is 140 liters divided by the specific gravity of water is often taken as 1. So the value is 0.140. Next, coming to the volume of admixtures. You know the mass of the admixture is 7 and you know the specific gravity is 1.145 into its 1000. You will be getting the answer as 0.006 meter cube. So far it is clear. Next, coming to the volume of all in aggregate. All in aggregate means total aggregate. Okay. See here, A means what? See here, A means volume of concrete, that is the total concrete. Okay, B means volume of the cement. Are you clear? See, A is volume of concrete. In the total concrete, you are going to minus the cement, water, and admixture. Remaining what you will be having? You will be having the aggregate. Okay, it may be a coarse aggregate, it may be a fine aggregate. Okay, in total quantity of concrete, you are going to deduct the cement, water, and then admixtures. That is why you see the naming here. It is mentioned here as A minus B plus C plus D. You can also write it here as volume of concrete minus whole of volume of cement plus volume of water plus volume of admixtures, and then you can close the bracket. You just write it like that, then only it will be understanding for you. Okay, so once you deduct those values from the total volume of concrete, you will be getting the total aggregate value. Okay, total aggregate means it has both fine aggregate and coarse aggregate. Okay, the total aggregate values here taken as what? 0.743 meter cube. By using the calculations, we found that. Next, mass of the coarse aggregate. So you found the total volume of the total volume of the aggregate. From that, you have to calculate the mass of the coarse aggregate, that is the weight of the coarse aggregate. For that, what we are going to do is you are having one formula here: volume of the total aggregate into the volume of the coarse aggregate into specific gravity of the coarse aggregate into 1000. See here, volume of this is the total volume of the aggregate. In the total volume, you are having only 0.56 only you are having coarse aggregate. Remaining 0.44 is fine aggregate. This is the total volume of the coarse aggregate. Okay, this is the total volume. In this total volume, 0.56 only coarse aggregate and 0.44 is fine aggregate. Okay, next you will be getting this as kilogram per meter cube. Next, I have to convert this as mass. This is in volume. So to convert this as mass, what I am doing? I am going to multiply the specific gravity along with the standard unit weight of the water. That is the specific gravity of fine aggregate and coarse aggregate in the question is given as 2.74. By using this condition, you will be getting the mass of the coarse aggregate and fine aggregate as 1140 kilogram and 896 kilogram respectively. Okay, so be clear about the two different things here. Okay, the first one is you should know this. Okay, here you should know the concept. You should know three concepts here. One is this mass by volume, that concept. Unit weight is equal to mass by volume. This unit weight can be written as specific gravity into standard unit weight of water. Okay, this concept. And coming here, this is the total weight of total volume of the concrete, not weight, total volume of the concrete can be it should be deducted by volume of cement, water and admixtures, then you will be getting the total aggregate volume. You are getting here volume, not mass. You are getting here volume. Okay, next moving on to this step. Here you should know this also. Volume of the total aggregate is 0.743. In that 0.743, only 0.56, that is only 56 percentages coarse aggregate. Remaining 44 percentages fine aggregate. Into its specific gravity and the unit weight will give you the answer in kilogram. For that purpose only you are doing this. Otherwise, you can just multiply and get it as in meter cube itself. Okay. Okay, next coming to the mixed proportions. So you found the water, liter per meter cube, cement, kilogram per meter cube, fine aggregate, coarse aggregate, chemical admixtures. You may ask me what is this meter cube? This is with respect to 1 meter cube of concrete. For 1 meter cube of concrete, you require 7 kg of chemical admixtures. For 1 meter cube of concrete, you require only 1140 kilogram of coarse aggregate. This is the concept, okay? This is in kilogram only, 1140 kilogram only. This per meter cube refers for per meter of concrete cube. Okay, that is the thing here they have given here. And the mixed ratio is often taken as cement is to fine aggregate into coarse aggregate. Okay, so the cement content here is 350. Okay, 350 is to fine aggregate is 896 is to coarse aggregate is 1140. Am I right? So what you are doing here? You have going to divide these three values by 350, because the first value should be often keep it as 1. Okay, first value it will be cement. So I'm going to make this as 1. For that I'm going to divide the whole value by 350, because the value of the cement is 350. If I divide 350 by 350, I'll getting the value as 1 what I needed. Okay, so and then I will be dividing this 896 also by 350. Then I'll be getting the as 2.56, and I'm dividing this 1140 by 350, and I will be getting the answer as 3.26. Okay, so this is your mixed ratio. Okay, this is your mixed ratio. Okay, so we have successfully discussed about the mixed design procedure when we are using the super plasticizers. Okay, next we are also going to discuss about the mineral admixtures. That is, we are going to replace the cement, right? If it is a chemical admixtures means you are going to replace water. If it is a mineral admixtures like a fly ash silica means silica fume means you will be replacing the cement content. So we will be discussing in the next coming classes. So thanks for watching. Keep watching these videos. Thank you all.